In this video, we'll look at how you can incorporate optional inputs with default values into the function M files you write in MATLAB. After studying this video, you should be able to incorporate error checks on the inputs to a user-defined function and use optional inputs with default values. Both of these will make your functions more generally applicable. So why do we want to do this? Well, like I just said, we want to write function M files to be as general as possible so they can be reused for a variety of applications. Also, we want to write function M files that can be used by others without requiring a thorough study of your code. Remember that engineering is collaborative, and most of the work you do will be in teams, so that includes doing mathematical modeling with MATLAB, and writing more general functions makes that easier to do. Also, we'll use this opportunity to develop a better understanding of how MATLAB's built-in functions work and continue to develop our programming skill. So we're going to revisit the bisect basic function that we previously developed and make the following improvements. We will check to see that the user supplies enough inputs for the function to work. We'll also check to see that the initial bracket includes a sign change. We'll allow an optional input for the stopping criterion, remember that's epsilon s, but we'll include a default value. We'll do the same for the maximum iterations. And lastly, we'll anticipate a possible division by zero problem and put a check in there that will make the code a little bit more robust. In other words, less likely to crash when it shouldn't. So let's look at some code that implements the first 4 of these improvements. So here is a modified code, modified bisect function called bisect defaults that implements some of those improvements. If you look, the first thing you'll see is we've added to the input list ES and maxIt. Those will be variables for the stopping criterion and maximum iterations. We've also added this new variable called varargin, and that's short for variable number of arguments input. And it's a special MATLAB command actually that's what allows us to have a variable number of arguments. It also handles the cases where users input additional arguments, and we can use that as a way to pass parameters to the function, and we're going to talk about that in another video. But for this video, what it does is it makes it so it's optional for the user to input ES and maxIt values. The function will still run even if there's any number of inputs once we include the varargin variable in that input list. So I've made some changes to the help comments, and now let's look at, now that we've included varargin, let's look at some if statements we've added to incorporate the defaults and check some errors on the input. Without the varargin, the MATLAB will exit the function if there's too few inputs by itself. But with the varargin that allows a variable number of inputs, we have to be explicit about how many inputs, what's the minimum number of inputs the function needs to run. And for this bisection method, that number is 3. We need the function and the lower and upper bounds of the initial bracket. So I've added here in line 18 an if statement that uses this MATLAB command called error to exit the function and output a red error to the command window with that error message. The next thing that I've done is added another error check to make sure that our initial bracket includes a sign change, because if there's no sign change, then there's no root in the initial bracket, and the bisection method won't converge. So I've calculated our test value, and if that test value is greater than or equal to 0, we're going to output an error that says that there's no sign change in the initial bracket. So the person using this function, or ourselves, would need to modify that initial guess so we make sure that it encompasses a root. The next two steps are to set default values for the stopping criterion and maximum iterations. So if we look at the stopping criterion, we'll say if there's less than 4 arguments, or there's no, the isEmpty command checks if there's just an empty bracket input for ES, or an empty matrix input. And I'll talk later in the parameters video, the next video, about when that is likely to be the case. Then we're just going to set a default value for ES equal to 10 to the minus 6. And then the same thing for the maximum number of iterations. We will set a default value of 50 if there are less than 5 arguments to the function, and the maxIt variable does not have, or the maxIt variable does not have a value. And another important thing to notice is this new variable nr. Again, that's a key special MATLAB name, variable name, and that goes along with var again. When we're using var again, nr again is a variable that's automatically created when the function is called, and it counts the number of inputs that were actually inputted to the function. Moving to the next section of code, we can see one other modification I made just to check for the case where we might have a division by 0. If we look at our EA calculation, we see we're dividing by x root. And so there's the possibility, which we would hit in particular if we had an initial bracket of xl equals -1 and xu equals 1 or something similar, that x root could be 0. And what we'll do in that case is, we know it's unlikely we'd be using the bisection method for a problem where the root actually is 0, because that would probably be something that we could solve analytically, or that it would just be obvious. So in the case that it's equal to 0, we will just skip that error calculation and move on to the next iteration. And so the way that I've implemented that is by saying we are only going to calculate EA here if x root is not equal to 0. So if x root is not equal to 0, then we calculate EA and continue with the bisection as usual. So let's look at an example of what we can do with our new, more robust bisection method. And this is a study to look at the performance of the bisection method and see how does the number of iterations that are required to converge depend on that stopping criterion. So what this example does, and I would encourage you to download the M file from the video folder and run this, perhaps run it in the debugger and make sure you understand how it's working. But basically we set up a vector of ES values, and then we're going to pass them one at a time as the 4th input to bisect defaults. And notice I have no 5th input, so that maximum iteration value is the default of 50. So it'll loop through that for loop, call the bisect defaults function for each of those values of ES, ranging from 10 to the minus 3 to 10 to the minus 8, and then I generated a plot. Note I used the semilog x command to generate a plot with logarithmic axes on the x-axis, and you'll see why in a minute. Here's the plot. Here's our logarithmic axis. And I did that because since we're changing ES by orders of magnitude, in order to see the variation of what's going on, we can use that logarithmic axis. And we see that as we ratchet down the tolerance, or as we decrease ES, so ES is decreasing here, going this way, we see that the iteration count goes up. And that's not too surprising. The tighter the tolerance, or the more precise the stopping criterion, the more iterations it takes for the bisection method to converge. And this is an example, our first example, really analyzing the performance of a numerical method. And we will spend time in this class doing this quite a bit, both in video examples and in programming assignments and other activities. And that concludes this video.